Hi everybody, thanks for watching. In this video, I'm going to go over several examples of writing formulas for binary ionic compounds, still no transition metals. Remember from the last video that when writing ionic formulas, it's all about balancing charge. If you've got a +2 calcium ion and a -1 fluoride ion, it's going to take two of those fluorides, so they add up to a -2, balancing out to +2. This makes your final formula Ca1 for the 1 calcium, F2 for the 2 fluorides you needed. There was, however, one important detail we left out of the last video, and that is, how are you supposed to know what the charges are going to be? I told you calcium was a +2 and fluoride was a -1, but when you're writing formulas for yourselves, you're going to have to know how to find that information on your own. The good news is that we've pretty much already explained how to do this in a previous video. It all goes back to valence electrons. So let's bring back our little cheat sheet for how to figure out the number of valence electrons an atom will have based on the column that atom is in. So let's start by labeling some important information on this that should look pretty familiar. The first thing being our separation line between metals and nonmetals. Metals on the left, nonmetals on the right. This is really important because metals all do a certain thing when forming ions. They all lose whatever valence electrons they have, meaning all the metals will be positive, whereas nonmetals do the opposite. They gain valence, meaning all the nonmetals will be negative. So, if you need to know the charge of an atom that lies in this first column, because it has one valence, it will lose that one valence and become +1. Or in the second column with 2 valence, it'll lose those 2 valence, becoming +2. We still skip over the transition metals for now. Jumping over to aluminum with 3 valence, it will lose those 3 valence, becoming +3. On the non-metal side, we'll start with the noble gases, which don't do anything. Remember, they already have the perfect electron configuration. But if you're in this column with 7 valence, you want to gain 1 electron to be like a noble gas. So all these atoms will become -1. If you have 6 valence, you want to gain 2, becoming -2, or 5 valence, you want to gain 3 electrons, becoming -3. We've left out some atoms here and down in this location because they either don't form ions or they don't do it in a predictable way, but make sure you make some notes about these predictable charges because it's going to make your job a lot easier when you start writing formulas. Now we're ready for our first example, so let's start with potassium oxide. Step 1 is to write the 2 symbols, K for potassium, O for oxygen. Step 2 is to look up the charges. Potassium will be here with a +1. Oxygen is here with a -2. I recommend you label those so you don't lose track. I'm also going to bring back the scale to help visualize whether those charges balance. You should see pretty easily that a +1 does not balance a -2. But if I had a second potassium, now there's 2 +1s, making that total positive a +2. Which does balance out to -2, making my overall net charge 0. This is what we're trying to achieve. Now my subscript for potassium is going to be 2 because I needed 2 of them. My subscript for oxygen is 1 because I only needed 1 of them. Get rid of everything you don't need, making the final formula K2O. Here's a second example. Let's try aluminum bromide. Symbols first, AlBr. Look up the charges second, +3 and -1. Use the scale if it helps you see if the charges balance. +3 and -1 definitely don't balance. But if I added a second and a third bromide, now my total negative charge is -3, which does balance out a +3. This makes the net charge 0, and again, this is what we're trying to achieve. My subscripts on the formula will be 1 for the 1 aluminum, 3 for the 3 bromides. Get rid of everything you don't need, making the final formula AlBr3. And finally, let's try calcium phosphide. Symbols first, Ca and P. Charges second, calcium is a +2, phosphide is a -3. On the scale, you should see that a +2 does not balance out a -3. You might also notice these numbers are a little bit trickier. Let's just try adding a second calcium. Now it's a +4, still doesn't balance that -3. What about a second phosphorus? Now it's a -6, which still doesn't balance out a +4. Finally, with a third calcium added in, I have a +6. Balancing out a -6, my net charge is 0. Since it took 3 calciums, my subscript here is a 3. 2 phosphides, so my subscript here is a 2, making the final formula Ca3P2.